Hello, everyone. We are continuing the advanced topics in quantum field theory seminar. Today, I'm going to switch gears from the kinds of things we've been talking about so far over the previous weeks, and we are going to talk today about thermal quantum field theory. So, quantum field theory used to discuss statistical mechanics. And at the end, I'll introduce you to some of the techniques in using this thermal QFT for superconductivity. Let's continue. So, a majority of this time is going to be spent on making this a introductory kind of lecture to thermal QFT. So I'll be going over what the thermal density matrix looks like and what the functional integral form of it looks like. And I'll talk about actually extracting observables such as electron density or current density. And then at the end, I will talk about an application of this formalism to analyzing superconductivity. Okay, so some of the prerequisites for this course are here. Basically, I'm going to assume you know about density matrices, the grand canonical ensemble, and you're somewhat familiar with second quantization approaches in quantum mechanics. So ladder operator stuff. Here's a little picture of the grand canonical ensemble. There you go. Can everyone see my mouse or no?
Yes.
Yep.
Yes, great. Excellent. So first, I'm going to talk about the thermal density matrix. Z here is the partition function as a function of, say, the chemical potential mu and the temperature T. The partition function can be written as the trace of the thermal density matrix, rho, where I give rho here. It's the exponential, basically, of the Hamiltonian, where beta is equal to 1 over the temperature, essentially. And here, I am absorbing the chemical potential term into my definition of the Hamiltonian. Here, I have a lattice version of the Hamiltonian, where I and J are lattice sites, but soon I'll be interchanging between this and a more continuum notation. Just for now, just know that I and J refer to spatial locations. So in the continuum, these sums will turn into integrals, and for example, this Tij matrix will become the gradient squared, our kinetic energy term, plus some arbitrary, potentially arbitrary other terms that one might decide to add to their Hamiltonian. The second term here, by the way, is an interaction term. For those of you who have covered second quantization, this is a form of the interaction term for two-particle interactions. By the way, feel free to stop me with questions, and I'll occasionally ask if there are questions.
Can I ask something?
Sure.
So it's the Tij minus mu with the square bracket. What is it? Is it just a number?
Yeah, it's just a number that is dependent on I and J.
Oh, okay, sure. That's fine.
Yeah, the operators here are the A's, the AI dagger, the AJ, etc. If you like, some people refer to the Tij minus mu as the matrix element Okay, so the chemical potential can be used, you can vary this parameter mu to vary the electron density or particle density in your system. And typically we choose the chemical potential to, reproduce the experimental average electron density we see in a solid. So what I've written here is the Hamiltonian expressed in the form of second quantization using these, ladder operators. But we can always choose to express H in a different basis and to take this trace in a different basis. So I'm going to briefly talk about coherent states. Even though these second quantized ladder operators, A dagger and A, are not Hermitian operators, we can still find left and right eigenvectors for these operators and associated eigenvalues. It turns out that this state phi with this form, the exponential of some numbers times a set of creation operators, acting on the vacuum state, this is one such eigenvector for, in this case, the annihilation operator. So with this definition, you have a eigenvalue phi sub j in this definition. This parameter xi changes sign depending on whether or not you're working with bosons or fermions. Similarly, this is the bra. You basically define it equivalently. I forgot the summation, the sigma summation, but you can pretend I'm using Einstein's summation. And here, the bra phi is a left eigenvector of the creation operator. So recall that these indices I and j in general can be arbitrary, but for now I'm taking them to be spatial indices. So are you at point I in space, at point j in space? One thing to note is that the bra, the eigenvalue, is the complex conjugate of this phi j. And it turns out that these coherent states have overlaps with each other. Phi prime is equal to this exponential. You'll notice that this is not equal to, delta phi prime. This is not an orthonormal basis. These two different basis vectors actually have finite overlap given by this. I'm taking this discussion, by the way, from Altland and Simons, page 158. Okay, so we are going to use these coherent states to turn our Hamiltonian into a path integral or a functional integral. So if you recall, we have this Gaussian integral identity where I haven't specified this constant c. In this case, it's something like 1 over square root of pi or 2 over square root of pi, something like that. Later, I'm going to start ignoring the c's or absorbing them into this measure here, d phi. So similarly to this identity, the coherent states that I was just talking about also have what you may know as a resolution of identity. So the identity operator can be written in many ways. You can write the identity operator using any basis you like. For example, you can write it using the occupation number basis. So it's the sum of outer products of the occupation number basis vectors. Or you can use these coherent states I was just talking about to write I. Turns out it's a little more complicated because these states are not orthonormal. That's why you need a weighting factor here.
Sir, what's the trajectory of the sun?
That's not relevant. Okay. Yes, Hank. All right, so the resolution of identity looks like this for the coherent states. If you recall, the quantity that I'm telling you we're interested in right now is this partition function, the trace of the density matrix rho. We can take it in any basis we want. We can take it in the energy basis, so the basis where the Hamiltonian is diagonal, in which case, you get the trace of the thermal density matrix being of this form, where H has now been replaced by just numbers or
so can you
eigenvalues.
speed up a bit? Can you slow down a bit? I'm kind of lost.
Do you have a specific question?
No, it's just, could you slow down a bit? It's kind of going quite fast.
Sure. Okay, so let's see. If you recall, here I have defined the thermal density matrix rho, which defines, in general, mixed state of our physical mechanics.
So can you speed up a bit?
H. Now, having reminded you definition, we can take the trace of this density matrix in any basis we like. As an example, here's the energy eigenbasis, where this operator is diagonal. So if we're using the basis where the Hamiltonian is diagonal, this means we can evaluate this. The energies E pop out like such. Similarly, we can evaluate the trace using these coherent state basis vectors that we've been working with. So it's not as nice as the diagonal H basis, but we typically can't actually diagonalize the Hamiltonian. If we could, we wouldn't have to go to so much work. So here I have defined this measure of coherent states. And for now, I'm going to just call this big D of phi naught. We have the overlaps. And here we have the matrix elements. Note, again, that this weight term appears. And, okay, so other people are saying the pace is actually fine. But, again, feel free to ask specific questions whenever they pop up. So the coherent states not being orthonormal. Go ahead.
Why do you call it 0, I?
I am... so the I is the relevant spatial index for the spatial degrees of freedom. And I'm going to be using more resolutions of identity. So I'm going to be introducing more variables phi soon. So I'm referring to these as phi sub 0, comma I. Later on, I'll be introducing phi sub 1 comma I, phi sub 2 comma I, phi sub 3 comma I, etc. But
Okay.
either way, either way, this is just an arbitrary variable. So I could have called this dkek or dhank. Okay, so this term, again, is to take care of the overlap between coherent states. And here are the matrix elements appearing in evaluating this trace of the thermal density matrix. I'm going to absorb this constant C into the definition of the measure from now on. Okay, so what follows is a fairly technical derivation. I'll have a reference for the derivation soon. It's again this textbook by Altman and Simons. But it follows basically the same derivation of the path integral formulation that should have been covered in the seminars a few weeks ago in this series. So let's introduce some fun variable names instead, just to show you that, you know, the variable names are arbitrary. I have d phi kek here. I have, again, this overlap term. So instead of 0, I have kek, just to show you, you know, the arbitrariness of the labeling. And what I've done here is I've separated this e to the minus beta h term into e to the minus beta h over 2. Sorry, I believe I messed up this. I shouldn't have both to the power 1/2 and to the beta over 2. So ignore this power of 1/2 here. Same here. My bad. Other than that, so ignore these 1/2s. Other than that, I've separated this term from here, e to the minus beta h. I've separated it into e to the minus beta h over 2 times the identity times e to the minus beta h over 2. Now, going on, I can introduce, for this identity operator, I can introduce another resolution of identity. So instead of just d phi kek, I'm now going to introduce another one of these coherent state resolution of identities with a different variable for fun, to show you, you know, you shouldn't be afraid of the naming scheme, the labeling scheme, calling it d phi Hank. Hello, Hank. I know you're in the chat.
Hello.
Yeah.
Yep, go on.
So I have d phi kek, d phi Hank, and I have the necessary overlap terms in the resolution of identity for phi kek. I have the same necessary overlap terms for the phi Hank variables. And now I've separated this matrix element into a multiplication of 2 different matrix elements. Again, my apologies. Ignore this extra 1/2 here and here. But as you can see, I now have a product of 2 different matrix elements. And I can continue this process. Don't ask me where part 2 of the thermal path integrals went. It's on a need-to-know basis. Iterating insertions of identity. So iterating this process now instead of Keck and Hank, I'm associating an index alpha here to keep track of the different resolutions of identity. You'll note that products of exponentials are equal to the exponential of the sum of these terms. So here I've brought together all of those products of the overlap terms that are necessary when using the coherent states. And I have done this iteration n times. These are, in the second line here, these are all the different matrix element products that come from this process. And this is the same thing that you do when doing regular path integrals in quantum mechanics, which was covered a few weeks ago. Okay, so here I've correctly written down the terms. The key thing that's done in path integrals is to take this n parameter to be large, to do this for larger and larger n, so that we can make some clever approximations of this exponential operator. So let's analyze one of these terms, where h is given by say a sum of two operators, a quadratic term in these a fields, or these a operators, and a quartic term in these a operators. We're going to, having done this process a lot, we're going to take n large and we're going to expand. Very similar to what you do when working with regular path integrals. For this term, we expand the exponential. We have 1 minus beta over n times our Hamiltonian, plus higher order terms in 1 over n, which we are going to disregard shamelessly because n is large. Okay. Does anyone want to ask anything at this point?
Hi.
Just something. Yeah, actually, I want to say something kind of important here in the step that you're doing, because in path integrals, when we do this, inserting a bunch of resolutions of identities, and then we expand the exponential, what we're doing is that we're actually dividing time intervals, and we're treating the time interval in infinitesimal, right? But here, yes, you have to basically do something very similar here, right, as you've said. But yes, the fact is that you have to insert resolutions of these coherent states, and these coherent states have to be close enough such that n, the difference between the n's that they have, the number of particles that they have, occupied particles that they have in these coherent states, are small, so that you can sort of treat like beta over n as this infinitesimal time step, so that you can expand, because right.
So you're saying that so you're saying that these operators A have to give small terms when acting on these coherent state vectors.
Well, not just that, but also the overlap between, after you act these operators on the coherent state on the right, and the overlap with that on the left has to be small. So that's the whole point.
Is it not kind of like you're essentially minimizing, like the path integral, you're kind of smoothing the function along, so any terms that are too great, the overlap's going to become so small that it'll essentially turn your term to zero, right?
From the treatment that I saw of a similar topic in Alex Kamenev's book, the finite overlap of these coherent states actually serves as a convergence factor that ensures that the path integral converges.
Yeah. Like, for example, in the measure that you've defined, like the d phi, whatever, each product of those comes with like e of minus phi squared. So that
Right.
helps a lot
These
with
terms.
convergence. Yeah, exactly. That helps a lot with convergence.
Yep.
Yeah, but the point is just that to expand the exponential, you have to sort of control beta over n, right? But then if you're taking n to be like completely fixed, you're in. Are you in canonical ensemble or just grand canonical ensemble? Is n fixed?
So this n, this big N, is not the number of particles in the system.
Oh,
This
right.
big-
Okay. Yeah. Mhm.
It's the time step, right? Like your number of separations, like resolutions.
Sure. It's
Right,
it's playing the role of the time step, this beta over n.
Okay. Yeah. So
So-
it's just the notation kind of tripped me up.
No worries, no worries. Clearing this up is good to do now.
Okay.
So these overlaps, I am not expanding at all, right? These
Mhm.
overlaps here are just here. The Taylor expansion that I'm doing right now is only on this e to the minus beta over n h term. And so
Okay.
since this n is not the number of particles in the system, it's the number of times I've done this resolution of identity, I can do this enough times such that n is much larger than any eigenvalue of h. Admittedly, h is in general an unbounded from above operator, but we are condensed matter people. We are not going to worry about that.
Yeah. I mean, the bottom line is that you're taking, because in path integral formulation, you have a boundary condition, right? But here you're doing something similar, right? And you have to be careful that you pick a compact boundary condition so that, you know, if you discretize the entire thing, they sort of get closer to each other, like these coherent states.
If you're thinking about the boundary conditions, then these terms here that connect to the coherent states appearing in the trace, this term on the left and this matrix element on the right, serve as the what appear as boundary terms.
Yeah, no, I mean, like what these phis can be, you need to put a constraint on that. Similarly to the path integral, you have a finite time interval, right? So here you have to.
Yes. So the finite time interval here means that this n only, or this, you'll see what corresponds to the finite time interval.
No, I know what it is. It's the value of phi. But what I'm saying is that you need these phis, which can be like general complex numbers, right? You need to bound them in a disk, for example. Because if you don't, then you can just discretize the entire complex plane and you won't get anywhere, because you can just, you have even division, and you can tile the entire complex plane, and you won't be able to do the Taylor expansion of h, of e to the h, basically. That's my point. So like the states won't get closer together, but if you put everything on a disk, then yes, it will. That's my point.
But the problem with doing that is then this resolution of identity isn't quite true anymore if we're bounding where phi can be. I suppose that just means we redefine this constant c.
I think because no, I think it can still be done. I think it can still be done. You just have to, you know, redefine what you mean by integrating over a field, right? You're integrating over like a basis function in the disk, either that or you're integrating over the basis function in the entire plane. But
Well, when you do regular path integrals, it's not like you bound the x and p basis expansions.
no, but we're bounding the time interval.
Sure, I'm bounding the time interval, but these phi's are not the times, right? These phi ket and bra pairs correspond to basically the x and p expansions in the regular path integral. They play the same role as the x and p basis expansions.
Okay, you know what? Let's save this for another
Sure.
time.
One thing. So
Yes.
you're letting these phi vary over the entire complex plane, right?
As I've written it, yes.
How do you know that it's not that the resolution of identity that you did earlier is not like overcomplete or?
It is overcomplete. That's why there's this weighting term here.
Yeah, even with this weighting term. That's because it's not orthonormal.
Right.
So you make it orthonormal, but it could still be overcomplete, right? It could like.
Yeah, that's fair. I will simply refer you to the Altland and Simons textbook, chapter 4, because they deal with they deal with this a little bit more thoroughly than what I'm presenting.
Okay, sure.
But they do talk about the overcompleteness of this basis.
Okay. Thanks.
Wait. I'm sorry that there's this barrage of questions, but like just one last thing because
Sure.
time and I quite lost track of like what is being calculated. I think what is being calculated is trace of like exponential of negative beta Hamiltonian. Is that the case?
Yes.
That's like the thing being calculated currently, right?
Right now, that is
And,
the thing being calculated.
What is the reason for calculating it again? Like what's the motivation? I lost track of that.
The motivation is that if you're familiar with statistical mechanics, you can extract expectation values of observables by taking derivatives with respect to the partition function. And so by calculating...
Partly my bad. Okay.
No, it's okay. So by calculating this...
Okay. It's just that, like, I'm like largely unfamiliar with like statistic mechanics, so I think I'll just like wait. It seems like a central quantity to be computed. I'll just, yeah. Okay, thanks. I'll just stop.
No, it's okay. It's a good question. Okay. So, as I mentioned, we're analyzing one of these terms, these matrix element terms that appear in the expansion. And in the context of this presentation, we are assuming that this Hamiltonian is bounded both from below and above. That's because if the electron has enough energy in your condensed matter system, it's just going to zoom outside of the solid, and you're never going to measure it anyway. And so that means since H is bounded from below and above, in this effective description, we can take n large enough to justify this Taylor expansion and truncate it to just this 1 over n term. And we can analyze this quantity term by term. We can look at the 1. And so this is the overlap of phi's at different alpha primes here. If you're familiar with the path integral approach, then this is the overlap of the phi variables at different times. And we can just use the definition of the coherent states to write down what this matrix element is. This is from the definition I showed you earlier. we can look at the next term. I'll forget the M for now. You can reinsert it if you want. Because the coherent states are left and right eigenvectors of these creation and annihilation operators, we can use the earlier definitions to simply move this creation operator to the left, apply it to this phi coherent state, move this annihilation operator to the right, apply it to this coherent state, and this extracts the field phi alpha prime at these lattice sites I and j. And once these terms have become eigenvalues, we can just factor them out of the matrix element, and we get back this overlap term. I've highlighted it in blue. We can do the exact same thing for this general interaction term. And I won't walk you through this one, but you get the exact same thing. You get eigenvalues that you bring out of the matrix element, and you get this leftover overlap term. Okay. So now we know that this K alpha is the sum of this plus this plus this. Well, there's a minus sign here. And here. And so because we've done this Taylor expansion to linear order in 1 over n, and we've already discarded higher order terms in 1 over n, we are going to reverse this process and re-exponentiate these terms in phi. We're factoring out this matrix element of the overlap of these coherent states at different alpha, which again is the time parameter. And we've re-exponentiated to this. I've written h here because what this h of phi is our original Hamiltonian, this ai, aj, plus other terms, having replaced these creation and annihilation operators by these fields, the bar phis and the phi alphas. Okay, so we've re-exponentiated this single matrix element. And here I'm reminding you of what we're computing. It's trace of e to the minus beta h. And I've included this mu dependence here, just to remind you that we can take derivatives with respect to mu to get different quantities like the electron density. And so this is just a reminder from a previous slide. We have the coherent state overlap terms and a lot of matrix elements from subdividing our Hamiltonian into small bits. Okay. Now, putting this all together, we get that our partition function is equal to this functional integral over a sum at these exponential bits, basically. First is the exponential bits that come from these first terms are from these coherent state overlaps. And the second terms, this phi alpha bar minus phi alpha plus 1, if you recall, come from these blue terms here. And the rest of this is our original Hamiltonian. Yes, Hank. Hank is mentioning in the chat. He's clarifying what he meant by boundary conditions. Due to the form of the trace, we impose either periodic or anti-periodic boundary conditions on the fields phi, depending on whether the particles are bosons or fermions. Okay. Glad I could clarify that. So now I've highlighted a couple terms. I've multiplied this term by d alpha over d alpha to make it kind of suggestive. Does anyone want to guess what this fraction is going to turn into?
Derivative.
Yes, that's exactly right. It's going to turn into a derivative with respect to alpha. And if you're familiar with the path integral form of quantum mechanics, this is exactly the same thing that happens that gives you a derivative with respect to time in the action. So if we make these substitutions I've highlighted here, then what I'm going to do is I'm going to replace this alpha with tau to make it more suggestive that this is similar to the path integral in quantum mechanics. Now, one thing that I personally didn't find too justified, but is commonly done in the literature, is that when we take this n to infinity, continuum limit, these Hamiltonian matrix elements evaluated at different alpha, we say that they become the same matrix elements evaluated at the same alpha. What that means is that we are assuming that these fields phi are smooth enough that in this continuum limit, they do not vary too quickly with time. And that is controlled, or this is kind of suggested, by the presence of this tau derivative, or this alpha derivative here. With the way that this pops up in the action, this derivative term suppresses large fluctuations in the phi fields with respect to alpha. So typically in the continuum limit, we make this substitution. And this is the same substitution that's done in regular path integrals for quantum mechanics. Yep.
I mean, you would expect Hij to become a functional of phi, right?
Right. I mean, that's
like a local functional, of course.
yes. In the continuum limit for both time and space, we expect Hij to be a local functional of phi.
So is that what you've written in the fourth point, or is this saying something more?
This is talking about the time portion. So it's becoming local in time.
Right. So it just says that it's like
Yep.
local. It's like a local functional. So it'll depend on phi and like maybe the first derivative of phi.
Right.
Okay.
I'm agreeing with you. Good observation. So the final form of the thermal path integral for the partition function here is that this trace becomes a functional integral over phi, where I've suppressed all these indices in the measure, times two exponential forms, just to make it all fit on the page. Here, instead of a sum over alpha, I've taken the continuum limit, and so now I have an integral over this variable tau from 0 to beta. Recall beta is related to our temperature. I haven't taken the continuum limit in space yet, so these I and j's still label lattice sites. But you certainly can take the continuum limit in space for this. We have a phi bar. We have a derivative with respect to tau, plus the quadratic part of our original second quantized Hamiltonian, the matrix elements thereof, times this phi j. So we have, even though due to, symmetries, we typically expect the microscopic h to be a local function of I and j, of space, as well as of time. I am leaving it general here because we can, and because for computing some quantities, it is useful to have this more general non-local form of h. So this is the quadratic bit, and this is the two-particle interaction bit of our Hamiltonian. This Vij could be a Coulomb interaction, it could be a Hubbard interaction, it could be whatever you desire. In fact, we can even have the Hamiltonian and the quadratic and interaction bits be dependent on time. Or in this case, it's really dependent on energy, because, again, this is thermal physics, not real-time physics. I believe, yeah, this is a summary so far. We've derived a path integral form for this trace, for the partition function. I'll note that we can only actually evaluate these analytically if we have Gaussian integrals, right? So if this quadratic term in phi were not here, or this quartic term in phi's were not here, we could certainly evaluate this first line if the second line weren't here. Connecting it to the talk last week, we can, in theory, evaluate path integrals of this form non-perturbatively using basically Riemann sums. So quantum Monte Carlo, where you just sample different field configurations phi, and you sum all those up. We can even include additional parameters in our Hamiltonian, like magnetic or electric fields or a pressure, including, time dependence in our Hamiltonian if we like. And before I move on to discussing more observables and response functions, does anyone have any questions or comments? All right. So I'm going to discuss next extracting different observables from the partition function, and via 3 different examples, hopefully you will get the idea of what is generally done. So in standard statistical mechanics, you'd get the expectation value of the energy from a variety of ways. Instead of taking trace of rho, you'd insert the Hamiltonian operator, and it is defined in this way, where I've written this trace in a specific basis. Sorry, this should be 1 over z times the trace of h rho. It's a typo there. But here I have the 1 over z factors. So this is the partition function, trace rho, 1 over it. Here I'm using the energy eigenbasis to write this trace as I did before. But instead of straightforwardly going through this procedure in the top line, we can actually get this equivalently by taking derivatives of the free energy, which here I'm just writing as the natural log of z.
Can I ask a minor question, which
Sure.
is kind of important for me to have a rough understanding like going forward? So,
Go ahead.
for one thing, I believe beta is like a formal variable. So is that correct?
Beta is basically 1 over the temperature.
Oh, okay. And temperature is the big T here?
Yes.
Okay. And the what is mu?
It's the chemical potential in the grand canonical ensemble.
Oh, okay. I am not aware of them, but like I'll just keep them in mind, kind of.
It's the parameter that controls what the particle density is in the subsystem you're analyzing.
I see. And the big E is like a general observable, like.
Well, in this case, this is the energy of the system you're looking at.
Right, and like you're specifying a system with mu and t, and like you're trying to like get the expectation value of the energy.
Yes.
And like you wrote that like that can be computed using the partition function that you computed beforehand.
Yes.
Not really like this. It's not. It doesn't have the trace at the moment. Oh, there it is. I was looking at the right
trace, and a trace can be taken in any basis. The trace is just the sum of the matrix elements of your desired operator.
Yeah.
And so I'm choosing, in this case, the energy eigenbasis of H. And so when you have, H acting on its eigenvectors, you just get the eigenvalues, which is this term on the right.
Right. Okay. Okay. Thanks.
Yeah. We can equivalently compute this expectation value of the energy of the system by taking derivatives of this term, which is typically called the free energy. You'll notice if you take the derivative of this f with respect to beta, you get a 1 over z from log z chain rule. Here I'm showing the derivative being taken. If you take the derivative with respect to beta of e to the minus beta e, you get minus e out in front. Basic derivative properties. So similarly, if I write h as a function of mu equals some operator tilde h minus the chemical potential times the particle density operator here, n hat, we can get the electron density via the standard way by calculating the derivative of f with respect to mu, which I go through here straightforwardly. I bring the derivative inside these matrix elements, and dd mu of e to the beta mu n brings down a beta and an n. That's why I have a 1 over beta here. And when this operator n acts on occupation number basis vectors, I get this red n here. And you'll notice this agrees with the definition of the expectation value of n. Yes, as Hank is saying in the chat, this is true. For these definitions, I am assuming h is time independent, or beta independent.
Can I just ask a question?
Sure.
This is, see this h of mu equals h minus mu n. Like, this is like generating functions, right? This is like more general than just a number density
Yes.
operator, right? Isn't it? Like, you can take any arbitrary operator and add an expansion onto your Hamiltonian, and you can also find an expectation value of that observable, that operator.
Correct. And that's what you do to extract more general things in
Yep.
statistical mechanics.
Cool.
All right. And I'll be talking about more general observables in a couple slides. But for now, I'd like to show you what this process looks like if you are evaluating this trace using the functional integral method. Okay. So recall from a few slides ago that the functional integral for our partition function takes this very big and messy form. So let's simplify this messy bit by absorbing all of these exponential factors into an action S of phi. If we care about the electron density that we computed a couple slides ago, the complicated bit we have to evaluate is the derivative of the partition function with respect to mu. And the only terms in the action that depend on mu are going to appear in this exponential term. Here I'm ignoring the bits that do not have any mu dependence in order to make everything fit on the page. But you can see the full action here. Voila. So despite this looking more complicated, this still is a derivative of an exponential with respect to a scalar in that exponential. And so dd mu acting on this. Does anyone want to guess what this looks like?
I don't know what to guess, but like in the isn't the square bracket like doesn't mean anything? Is it just a number there, or
It's just a number there.
I mean, in which case it should just be gone, right? If you take a derivative. Oh
Well,
no,
this is the derivative of
I didn't
an
see
exponential of that number.
Okay. Yeah. In which case, like the thing inside will pop out, right?
Right. The thing inside, except for this mu here.
Yeah,
the mu will stay up here. But everything else will be brought down. That's right.
Yeah.
So here, I do exactly this. In red, I highlight the bit that has been brought down by taking this derivative. So the expectation value of the electron or particle density in the system is going to be equal to this functional integral. The red bit is nu, gotten from taking this derivative with respect to mu. You'll see that if you try and look at an individual one of these terms, say if this were an integral over x dx, you'd have x times, I don't know, x complex conjugate times x times e to the minus s of x. So this is really just if you're familiar with statistics, this is a moment of this distribution e to the minus s. Because there's an integral over d tau and a sum over L here, it's more like a sum of moments. So these bullet points here discuss how basically this observable, the average density, isn't that interesting of an observable. Because this is, you see from the summation over L, this is a spatially averaged density. And let me comment on the role that this integral over d tau takes. Performing this integral over d tau from 0 to beta performs the thermal averaging that exists in the system. So you're averaging over all of these states that you would expect, all the fluctuations you would expect to appear in a thermal ensemble in a system. So that's kind of the role that this d tau from 0 to beta integral is doing, is having. Yeah.
Can you commute the functional integral and the integral over tau like that?
So you mean, shouldn't the integral over tau be inside
Yeah.
this d
Yeah.
phi?
Yeah.
We are going to assume that we can.
Okay.
This is justified because when you perform a measurement of the particle density of a system, you do not get infinity.
Okay.
Right. So since the quantity we're computing converges, I'm just going to kind of hand wave away the interchange between the functional integral and the integral over d tau.
So then the quantity inside the bracket is just like a it's like a trivial functional where you evaluate the function at some particular point, right?
Yes. Yeah. It's yeah, as I mentioned, this is like a x squared, or absolute value of x squared, times e to the minus s of x, where s is some function.
Yeah, no, S is a proper functional, but
Right, but this is just this is not a functional in the brackets.
yeah.
Right.
Exactly.
Minor question: is the n hat the density, or like what kind of operator is it?
It is the total particle density in your system.
Okay, cool.
But if you wanted to find instead of spatially averaging the density, so the sum over L here, if you wanted to find the site-dependent density, n sub L, then instead of attaching a scalar mu here, you would attach a site-dependent mu sub L, or a site-dependent chemical potential. So here, to remind you that this can also be a continuum theory, I'm going to write this in terms of a continuous volume and let the field's chemical potential be dependent on this continuous variable x. So similar to before, what we're going to do is compute the derivative of z with respect to mu sub y instead of just mu. So the notation and computing this derivative ends up being a little more subtle, because this is at a specific point in space, but this is an integral over all space.
So it's a functional derivative.
Yeah.
Yeah, because the thing inside the bracket is a function of mu, and you want the you want the functional derivative at some site
Yes.
y.
Yep. So this ends up being a functional derivative. I'm not quite
Okay.
using the usual functional derivative notation.
Yeah.
But you're right. This is now a functional derivative of mu at location y. Very similar to before, though. Performing this derivative extracts out this phi and this phi. But since the derivative is being taken with respect to mu at a specific location y, we no longer get this sum or integral over spatial variables y. So now we have a location-dependent density as a function of, say, mu and the chemical potential and the temperature. So just as before, we can evaluate it by computing this functional integral. That's not so easy, as I have commented before, but the expression is there. So to highlight the difference, here is a location-dependent particle density, and before we were looking at the spatially averaged particle density of the system. The spatially averaged particle density is much easier to measure because our measurement devices are large, and so typically we get a spatially averaged density from them when we use large measurement devices. But here we have a more microscopic variable. Sure, Chronum. That sounds fine to me. Let's talk about generic observables. More generic than the location-dependent density.
Sorry, I have a little question. Can you go back to the previous type?
Sure.
Yes. So in this functional integral, the last functional integral, this kind of looks like a propagator, right?
Yes. This has the form of a propagator.
Yeah. So, but then this is evaluated at the same point. So this is like
Sure,
a propagator
yes.
at 0. This like typically diverges, right? I'm sorry.
So the propagator evaluated at the same point diverges in regular quantum field theory, but what we're seeing here, of course, is that this will give us a finite answer because any particle density we expect to extract is going to be finite. And the finiteness is partially because we are working in the onset in d tau. Let's see. So this is an exponentially decaying action. Let's see. This is always going to be an exponentially decaying action. There is no, imaginary eyes here to make these terms oscillate.
Yeah.
Let's see. But perhaps we can save this discussion for later because as Chronum is mentioning in the chat, it would be nice to save some of the questions for closer to the end. Yeah. Okay. So for now, why don't we just take it as given that the particle density at a point is going to be finite. And we'll talk about generic observables. And I don't think that we'll be actually talking about superconductivity today because I have a meeting soon enough. But we can finish up this talk on observables. So in general, just like the previous two examples, the way to extract generic observables in a solid state system, or in a statistical mechanics sense, is to attach an arbitrary parameter, say p, to the desired observable in the action, and take derivatives with respect to the free energy, which is related to the partition function here. So we sometimes call z of p a generating function. And before, we already had a chemical potential in our Hamiltonian H. Now, for more generic observables, we don't want to introduce unphysical external fields. So for more generic observables that don't already have terms in H, we typically set the parameter equal to 0 after taking these above derivatives. Okay. As an example, we can talk about the thermally averaged current density. And in Schrödinger quantum mechanics, the current density looks like this, minus the minus psi gradient, psi star, I think. But let's just say it looks like this for now. And so we're going to attach a term gamma of x that's going to play the role of mu of x before, times phi bar times the gradient of phi to the action. So for this example, the current density, we are attaching, as I mentioned here, we're attaching a term gamma of x, phi bar gradient phi to the action, which means when we take a derivative with respect to the partition function, the relevant bit is this term in the action. Highlighted in blue is the, if you like, the Lagrange multipliers that we've added. Taking the derivative with respect to gamma is going to bring down everything except the gamma at that point y. And so very similarly to the previous case, we get that the current density is equal to evaluating this derivative, an integral over tau, everything we've seen before. And we have our desired observable in blue here, multiplying our action. And since there wasn't already a term coupling to the current density in the Hamiltonian, we're now setting this parameter gamma equals 0. Okay, so that is the example for the current density, the extraction of this observable. I can show you some pictures in superconductivity, but I don't think I have time for the full discussion because we are already close to the end of the time I've allotted for this. Yep. So I'll just show you some pictures to describe to you what superconductivity is. and then I'll have maybe 5 minutes at the end for questions. A superconductor, as you may or may not know, is a material that shows a couple properties. One of them is that as you vary the temperature, as you lower it, the resistivity of the material suddenly drops to 0 at a critical temperature. A normal metal has this behavior. It never drops to 0. The mechanism behind the transition in superconductors for the superconductors that we initially discovered is due to electron-ion attraction. As this electron in red is passing through a lattice of ions, it's, attracting the ions it leaves behind. So these get squeezed toward the electron. And the electron here, kind of away from it, behind it, then sees a region of increased positive charge density and is attracted towards this region. The picture is a little more complicated than what I'm showing you, but this is a fine physical picture without, worrying too much about it. Of course, to make quantitative predictions, you want a more quantitative description. The other major sign of superconductivity is what's called the Meissner effect. Above the critical temperature, a magnetic field applied externally, will do whatever it wants in the material. It'll pass through the material, etc. But when a material becomes superconducting, it turns out that the magnetic field is actually expelled from the superconductor. And what happens here is that when the material becomes superconducting, the photons in the material actually dynamically generate a mass. So the photons inside the solid are massive. Since photons don't like to have mass, they just avoid going into the solid in the first place. So they go around the solid. I can't talk about why this is due to time constraints, but I will refer you to Altland and Simons, Chapter 6. And the final picture I have is a picture of the electronic density of states as a function of energy. I have this for a variety of temperatures. At the highest temperature in the upper left, which is right at the critical temperature, it turns out there is a dip in the density of states. What this refers to is that some of the electrons are now pairing up into Cooper pairs and are no longer acting as usual free electrons. As you lower the temperature, so going down and up to the right, this dip gets larger and larger until you get far enough below the transition temperature that this turns into a full-on gap in the density of states. And what this means is that, or what this is telling you is that all of the electrons within this energy range, say negative 0.1 to 0.1, are basically paired up into Cooper pairs in the solid. Now, I had some slides, not too many, but too many to really go into, about just deriving the Ginzburg-Landau theory of superconductivity from microscopic thermal quantum field theory but I will have to refer you to for the details. It's too bad, too. My favorite transformation, the Hubbard-Stratonovich transformation, was in these slides. But anyways, I'll go back to this summary here. That is what I had prepared, minus a little bit that I can't get into because I have to go in about 8 minutes. But I will happily take any questions you all have during these 8 minutes.
Before questions, I think we should clap for Slender.
Yep.
Anyone wants to join
Good work.
me? Wow, nobody claps. This is like so customary for like more or less academic stuff, but okay.
Yeah, and as Gandul is asking, you can always talk to me about it later in chat. I just have a meeting and other things to do for now. Thank you, everyone in chat, for clapping instead of physical claps.
Virtual claps. I have the audacity to speak up and clap in front in my room alone, silently.
Thank you. I appreciate it.
That was very interesting, though. Thank you.
Hey, you're welcome. I know a lot of it was technical, but that's what you get in a advanced QFT seminar, I guess.
It's quite cool because, like, you go through the whole hassle of deriving the path integral, but you never actually really plan on solving it, right? You just want to use it to get your partition function properties so that you can find your observables. I just find that quite humorous.
Yeah, there are some techniques for actually evaluating the path integral that I had in the end part of the talk to actually...
I think you said if they're Gaussian problems, if they're Gaussian integrals, you can actually evaluate it exactly, right?
Yes. Yeah, which is the same for regular quantum mechanical path integrals. But of course, you can always do perturbation theory around the Gaussian part by Taylor expanding the non-Gaussian bits. Or you can just straightforwardly, but computationally intensively, evaluate with just Riemann sums. Does anyone have any questions? They'll have to, unfortunately, be short questions, or short answers to questions, but... All right, Johan. That's okay. I, don't have to give a lecture in 2 weeks.
Yeah, it's fine. Thanks for the talk, Slender. I just wanted to make a comment about the divergence of the coincidence density, like the local density.
Please do.
Yeah. So typically, when we evaluate like field operators, right, phi x and phi y, evaluate the expectation. What happens is that you get the inverse of your Hamiltonian in a free theory, and that's the propagator, the green function. And it's true that when you take just pointwise limits when x and y equal to each other, what happens is that there is a divergence, but we can regularize it because the pole is symmetric about positive and negative value. Let's say we're working with like real fields, for example. Then what we can do is that we can just regularize it using Cauchy principal values or stuff like that. That is one thing that I don't think the exponential will help, because in the minimum, around the minimum, the exponential is just a number. But yeah, anyways, I mean, there are ways to deal with that. That's not really a big problem.
Yeah, if you perform perturbation theory, I do expect you to get these divergences.
Mhm.
If you do perturbation theory around the free field theory. Other singularities can, of course, come from if your Hamiltonian has zero modes.
Mhm.
So I know some of these singularities would disappear. Evaluates the path integral non-perturbatively. But not all of them, because some of these singularities do spawn quasi-particles.
Yeah. That's true. Like, for example, the heat kernel expansion is sort of like, it is sort of perturbative, but it's a very smart perturbative expansion. And in that case, it's, when you take the limit of whatever is in the exponential going to zero, that's sort of like doing exactly this thing I was talking about, right? The Cauchy principal value and whatever, then that gets rid of the singularities or the poles that you would have encountered in perturbation theory. But yeah.
Oh, yeah. And so part of that is taken care of when you, have this 1 over z term. Some of the singularities that appear in the correlation function are taken care of by this 1 over z factor, which I believe is related to what you're referring to as the heat kernel regularization.
Yeah, that's right. So, the e, if we write z as e to the I psi or e to the minus psi or something like that, then anything that sort of has divergences, for example, the zero modes, going to be canceled by the 1 over z factor.
Exactly.
And you sort of take the limit of that going to zero in the exponential, and that gets you the heat kernel expansion. And that technique is it works. It also coincides with the zeta function regularization, which is nice.
That is nice.
Yeah.
And it is also kind of glossed over in the condensed matter community because, that's also partially why the convention is typically taken to work with this free energy as the natural log of z.
Mm-hmm.
So that, condensed matter people can kind of gloss over having to go through this heat kernel regularization by saying, oh, let's just compute observables from taking derivatives of this free energy. You get the 1 over z for free.
Yeah. I mean, that's also true in QFT, but
right.
That's because, we have this sort of thermodynamic understanding of, this is the free energy and this is the entropy, this is the whatever, and we just sort of apply thermodynamics to these systems. But at the end of the day, you still have to use these techniques, right? To make things more rigorous and precise, right? But
but yeah,